Section 3.2 on logarithmic functions. So a logarithmic function is just the inverse of an exponential function. So if you look at the equation log base A of x equals y, this is a logarithmic equation. The little a is considered the base, then you have x, and equal to y is what that is all equal to. Well, that equation is exactly the same in exponential form as me writing x equals a to the y power. And I'm going to show you a trick in a second on how to go back and forth between the two. So a log function with base 10 is called the common log, and it is denoted by log base 10, or most of the time there's no 10 there. It's understood to be a 10. So if you see a different number other than 10, that's where we run into a problem with our calculator, because our calculator is designed for logs with base 10. Later on in the chapter, we'll learn how to use our calculator for other bases, but right now we're going to use some properties. So here are the properties of logarithms. Log base A of 1 equals 0 is the same as in exponential form, saying a to the 0 power equals 1. Log base A of A equals 1 is the same as in exponential, a to the first power equals a. Log base A of a to the x equals x is the same as a raised to log base A of x equals x. And then log base A of x equals log base A of y is the same as x equals y. When a log equals a log and the bases are the same, you can drop the logs and solve the equation. So these properties should come pretty naturally in a second when I show you how to manipulate and go back and forth between logs and exponential functions. Next we have the natural log function. And natural log functions are used with base e. And remember, e is that crazy number 2.71818281828 on and on forever. So when we use base e with logarithms, we actually use the symbols ln, which stands for natural log. I don't know why it's not NL, that would make sense, but it's ln of x is understood to be base e. So properties of natural logs are very similar to properties of common logs. So the log of 1 is equal to 0 is the same as saying e to the 0 power equals 1. Natural log of e is equal to 1 is the same as e to the first power equals e. Natural log of e to the x equals x is the same as e to the natural log of x equals x. And then finally, the natural log of x equals the natural log of y. When a log equals a log and the bases are the same, we drop the logs and x equals y. So we're going to go back and forth between logarithmic and exponential form. Let me get rid of this here for a second. Log base 16 of 8 equals 3/4. So this is a logarithmic equation, and I want to rewrite it in exponential form. So the trick that I use to go from logarithmic to exponential is I use this little loop-de-loop that you saw there a second ago. You always start with the base, which in this case is 16. You go around to the other side of the equal sign and then back to the bigger base. So all this does is tells me what goes where when I write the exponential equation. I start with the 16, raised to the 3/4 power equals 8. So 16 to the 3/4 power equals 8 is the same as log base 16 of 8 equal to 3/4. There are times it's going to be beneficial for us to solve equations in logarithmic form. There are other times it will be beneficial for us to convert to exponential form. So you need to be able to go back and forth between the two. So this is our answer. We weren't solving anything or simplifying. We were just rewriting it in another form. Same thing for number 2. E to the negative 0.5 power equals 0.6065. So this is exponential, and I need to rewrite in logarithmic. So I'm going to start with the base and do my loop-de-loop again. E around to the other side of the equal sign and back to the exponent. So since this is a base E, I'm not going to use log, I'm going to use natural log ln. So the natural log base E of 0.6065 is equal to negative 0.5. Now natural log is understood to be base E, so I don't have to put that little e there. I can just write natural log 0.6065 equals -0.5, and that works just as well. Okay, number 3, we're going to evaluate this function, but we're not going to use our calculator. We're going to plug this e to the negative 2/3 power into the x, and we're going to simplify using properties of logarithms and natural logarithms. So when I substitute this value in for x, I'm going to have f of x equals the natural log of e to the negative 2/3 power. So I know that natural log is understood to be base e. Earlier, we had a property that said the natural log of e to the x power equals x. Well, the x in this situation would be negative 2/3. So anytime you see a big base and a little base that are exactly the same, they're going to cancel out, and we're just left with the exponent. So that f of x equals negative 2/3. You can even type this into your calculator, natural log e to the negative 2/3 power, and when you hit enter, you're going to change it back to a fraction, you would get negative 2/3. But the purpose here is to use the properties and not your calculator. Later on, when we have equations with variables in them, you're not going to be able to type that into your calculator and find out the answer. Okay, same thing for number 4. Log base a of x, and we're going to say that x is equal to a squared. So I'm going to substitute a squared into x. F of x equals log base a of a squared. Same thing here, even though it's a common log instead of a natural log. I have base a, a little a and a big A, so those are actually going to cancel out, and I'll just be left with the exponent. We had an example in the properties of logs that said log base a of a to the x power equaled x. So this is just going to be f of x equals 2. Okay, now we're going to be graphing these logarithmic equations. We're not going to do all these directions. We're just going to find the domain and range and then sketch. Or the other way around. We're actually going to sketch first and then find the domain and range. So if you type the natural log of negative x into your calculator, natural log is right beside the 4. We're going to type this into y equals, and we're going to get a table of values to plot our points. So we want to try to get about 5 points. You're going to have to get some decimals, just round them to the nearest tenth. So here are the points that I'm going to use. I just tried to get a variety of points. You'll notice that after -1, I don't have any more values than I can use because I've got errors in my table. Okay, so then I plot these points. So once my points are plotted, then I'm going to connect the dots. And you can see from the graph that it's going to keep going down. It's kind of hard to tell on our calculator, but it does continue to go down. So now let's talk about domain and range. So domain are the possible x values, and range are the possible y values. Okay, so for the domain, I think about from left to right, what is my graph doing? So I think about how far left is this graph going to go? Well, because the arrow is pointing to the left, it's going to go negative infinity. It's going to keep going to the left. So that's negative infinity. And then when I think about how far to the right it goes, it stops at 0 and it doesn't go any further. So that's why our domain is from negative infinity to 0. And anytime we use infinities, we make sure to use a parenthesis instead of a bracket. Okay, now for the range. So range is the y values from bottom to top. So think about how far down is this graph going to go. Well, the arrow is pointing down, so that means it's going to go negative infinity. And then I think about how far up the graph is going to go. Well, as this graph is going to the left, it keeps going up further and further. So it's going to keep going up to positive infinity. Okay, so our domain was negative infinity to 0, and our range was negative infinity to positive infinity. Okay, we're going to do the same thing on this example. Log of x plus 1, we're going to type that into y equals in our calculator. I'm going to go to my table and pick some values. So here are the ones I picked. You notice if you go above 0, you see some errors. So I plot my points. See, this one just gradually goes up and over. Now when you look at the graph of this one, it doesn't stop at 0. It actually goes over to negative 1 and then goes down. So this time when we're talking about the domain of our graph, from left to right, it starts at negative 1 and then it's going to keep going to the right, positive infinity. So that's from negative 1 to positive infinity. And then for the range, I think about how far down and up the graph is going to go. This one is going to go from negative infinity to positive infinity. Okay, last example, we're going to use the one-to-one property to solve. I've got log base 2 of x plus 10 is equal to log base 2 of 4. So, as long as the log and the bases are the same, when you have a log equal to a log, you're going to drop the logs and solve the equation as is. So now I've got x plus 10 equals 4, and if I solve this, I'm going to get x equals negative 6. So anytime it's a log equals a log, drop the log, solve the equation.